So welcome to our fourth lecture on AI. In our previous lecture, we looked at search in simple environments. So simple defined as we know where we are, we have very set rules, we have a fully observable state. Yes. Oh, we don't have a state. You don't have a fully observable state because you don't. Those guys graph is not.
Is it like turned on?
Oh yeah, that looks kind of. There's something missing here. Extension, or maybe just a switch. That also helps. Yeah, I think the switch. Flip. All right. So yeah, so we had fully observable, right? Deterministic, right? Static, right? Things don't change. And well, again, known environments, right? So like the Google Maps, where you assume there's no weather conditions changing, no road closures, no cars breaking down, and we have PC and we have screen. All right. So I will be moving towards using code spaces. So you can use Colab again. Remember, same notebook. I'm using my code space here, right? But you can use, of course, in Ortus, you can use the Colab.
Are you going to start using like the code features more?
Yeah,
okay.
Yeah. That's why I'm trying to move towards that. And yeah, speaking. So yeah, so Colab, and also notice there is a first homework, right? Maybe some of you noticed already, right? So as promised, you wanted the vacuum cleaner, you got a vacuum cleaner, right? So yes. So it's again, as usual, it's going to be relatively open, meaning, so you have developed an intelligent agent, but intelligent agent, in this case, it's a vacuum cleaner, right? You're going to have, for now, we're going to have an n by n grid, so square rooms. I'm thinking maybe I should maybe adjust to n MSM. It doesn't really change anything. So what is the room going to look like? It's going to basically have a whole bunch of dirt, right? So 0 means it's completely clean, right? Integers, for now, integers 1 to 9,000 will be some sort of dirt you can clean. If it's over 9,000, right, you can't. It's a wall. It's either a wall or such dirt that you cannot reach. You cannot go through it. Your vacuum cleaner will just basically die, right? So what can you do? You can move north, south, east, west, right? 4 directions for now, not diagonals, right? It's not smart enough at the moment, right? But there are some things. Movement is not free. Right, to make things more interesting, movement costs electricity. So you start with some battery, right, and it's going to round down eventually, right? Maybe it will we have enough, right? So there's going to be vacuuming, right? So you can cleaning costs something, and movement costs something, right? 2 things. There's 2 different costs, right? So you're going to start with some B units, right? And your goal is to clean as much dirt as possible. There are actually 2 goals, right? Primary goal, clean as much as possible. Secondary goal would be clean as many squares as possible. Again, these might not be completely, they might be related goals, but they're not the same, right? If you have one big square is 8,900 or 9,000 units of dirt, right? You move there, right? You clean it, right? But the rest of the room is like 1 and 2 squares of just very tiny bit of dirt, right? So you did you picked the lowest hanging fruit first, right? You got that, you clean the really dirty place, and then you say, okay, I'm done here, right? So 2 different goals. Also, I might actually add some extra goals. There is actually going to be some bonus challenge for those who really say, okay, this is too easy, right? You can add a multi-agent, meaning support 2 robot cleaner. Maybe this might be very interesting. I think second one is interesting. Detect whether there is some place in your room you cannot reach whatsoever with your robot, right? It's so dirty, right? There's a wall around it, you cannot reach it, right? That might be a good one. Right, optimization, of course, that's just general. So what do I want from you? Source code, right? Python is fine, but of course anything else. You can write in Rust or C++ or anything, right? All, pick your poison. Which one?
No, I'm just thinking just
C?
Just
C is fine. I love plain C over C. I don't like C++ actually too much. I like plain C.
so anything like more like assembly or
Well, if you really want to. I mean, I don't know why would you want to do this in assembly unless you really, want to practice your assembly skills. Yeah, sure. I mean, I'm not gonna stop you, right?
no, then you're getting graded.
Yeah, but well, the thing is, okay, well, I'm going to give you some CSV files. Right now, I don't have the CSV. I just have a simple example right now, right? Like this. Again, so comma separate file, really simple, right? So this is 5 by 5 room, right? So what I'm thinking, actually, I'm going to probably during this break, I'll adjust this a little slightly. I think what should make things easier, these extra things, energy, vacuuming cost, and battery, right, on starting position should probably be supplied in a CSV first, right, not in a separate file, probably easier, right, if it's all in one file, right, like the challenge, everything in one, right. So I'll put those 1, 2, 3, 4 lines first, right, so that might be easier. So again, any language, knock yourself out, right, as long as you can read the CSV file, right. I mean, UTF-8 or doesn't matter. It's probably just going to be ASCII, right? There's not going to be no fancy symbols, right? Nothing strange for now. I don't want to make your life too complicated, right. So what I want to do, of course, is source code. So what I want from you is source code. Yeah, a greedy search might be one idea, right? We'll talk about greedy search, right? Most of you have seen greedy search, right? A star, not necessarily. You might have done something else. There might be different approaches, right? So this is kind of like pre-open. So source code. What I do want is some short report, right? So since of course you'll be using, maybe you'll do it completely by yourself, but you'll probably get some documentation, AI assistance, things like that. I want to see some, a short 1-2 page report on this, or again, comments too, right? So again, if I get the source code, everything works, but there are no comments and nothing, I can't give you 10 then, maybe 7, I don't know, 6 maybe, right? So I want to know what is your, basically, I want to see,
right?
yeah, I want your process. That's what I want, yeah. If I see you actually, you tried something, maybe not necessarily everything worked, right? That's great, right? Because it's like this is the road, right? Not the goal. I mean, the goal would be great, right? But actually, what you did during your journey, right, would be what I want to see. Okay, right. So the only question now is, I right now made it 18 days to be 3rd of February, because I know some of you got the homework from me already in programming languages for the 30th, right? So 3rd is February would be 2.5 weeks. What do you think?
Good, so bad.
Super, right? Okay.
Just to elaborate, so this is mandatory.
Yeah, because the idea was that will lessen your load in the midterm.
So what is how the original one, did you change it already?
Which one?
The original.
Oh, the formula.
Yeah.
Right. So maybe. So my idea is this: like 4 homeworks, roughly 4 homeworks, right?
In the semester?
Yeah, during semester. Yeah, roughly 4 homeworks, not 7, not 8, but 4, right?
And an end project.
An end project, yeah. So that will come out with 5 actually, right? The end project will be group work, right? Yeah. Excuse me?
No.
It's
Great.
It's good. It's good. You're happy, guys. So the only question now, of course, the thing is, something like this you have to do on the midterm, right? The question is how much weight to give to midterm now.
Approximately like 2%.
If you want really heavy, 5% would be.
Yeah. Okay. Let's look at the formula. Right. Let's look at the formula. Right. Let's look at the formula. So grading. I like what you were thinking. Yeah. Yeah. To make things fair. Right. So lecture quizzes midterm. I think 20. 20 would be midterm. Let's do third. So let's lower it to 20, 30, right? Yeah. And 20 for these homeworks, I think, right? Yeah. So that's I think that sounds good. And of course, you still have the extra 10% for the report. So I don't know. I mean, this is. So again, so 20, 30 would be the final project, and then we have the 4 homeworks. Yeah. Again, why do I make myself do extra work? But well, it's fair. It's only fair. I'm making you do extra work, and I'm assigning myself extra work, right? Yeah. So 4 homework assignments, right? So each is worth about 5% of your grade. So each assignment you complete will be 5%. So each assignment is roughly, right? Percent of your grade. Yeah. Okay. That makes sense. So again, 11. You can get 11 technically again, right? Now, yeah. Of course, I could make it. I could lower the electoral quiz, but make it maybe again next year we'll figure out something. Maybe make things a little bit. Maybe I don't know. I'll adjust this maybe as it goes. Okay. I think this is pretty good compromise. All right. Let's go to the topic at hand. So search in complex environments. And so, or chapter 3, right? Or chapter 3 was just to find paths, right? Final state, right? But we have now so-called local search, right? We have some starting point, right? And we basically want to explore what's happening locally, right? So, let's look at the picture. I want to show you a picture. This is kind of, well, where's my picture? Not this hill climbing. Right, yeah. Maybe I can show you a picture. I don't have a picture here, unfortunately, the one I want to show you. But the idea is this, right? When you're searching locally, right? It's like that old joke about looking for keys, right? The drunk guy who's looking for keys, right? And he's looking around the lamppost, right? And the policeman asks him, why is he looking there? Right? He said, well, you know, what is he doing? He's looking for keys, right? But where did you lose the keys? I lost them in that bushes, right? And says, why are you looking here? Because it's bright here, right? The logic of the drunk, right? But anyway, so what I want to get at is that it leads to this part here, right? So oftentimes you want to find something called the global maximum, like the highest mountain in the world, right? But if you're looking in Latvia, right, you're not going to get behind far, you know, Gaiziņš is best you can do, right, within the confines of Latvia, right? So many algorithms have this problem, right? So how do you find if you're in Latvia, right, and you need the algorithm how to find the highest mountain or a hill, right? What's your approach? You can of course get a map, right? But if you don't have a map, right, you're in some unknown place. Right, and you want to climb up. You want to find something high, right? Maybe there's a flood coming, right? You want to get out of this place, right? You need some, protection. So, what kind of approach could you take? Well, assuming you can sort of like your eyes work, right? You can look up, right, and see which place is rising, right? You go towards the direction where the ground is going up, right? Maybe you assuming you have some horizon, you can see, right? You have some vision. I mean, again, let's say you're in the middle of desert area, right? You don't have your phone is not working, right? You just have your eyes, right? Maybe you have some balance. Maybe you have you can see, okay, which way is going up, right? So you would be doing what? You would be going to the place which is going up, right? As far as your eyes can see, right, you would be going up, right? And at some moment you see, okay, you're starting to go down, right? So look at this picture here, right? These two guys, right? They go up. If they are really short-sighted, they don't see those mountains here, basically, right? They think each of these guys here in this picture, right? They think they are at the top of the mountain, right? Because they don't see even the next guy, right? They only know this local mountain, that's the local high. So that's called local maximum. And this is a problem pretty much everywhere, in machine learning and AI, everywhere, actually in general, life solving. So whether what you have found, like your optimum, your best thing, is this actually like the world best? Like, are you the first in your village, or are you the first in Rome, basically, question, right? So, like I said, and if you have your search space, if the world is large, right, well, it might not be easily solvable problem. So there are multiple approaches how to solve this, right? So, again, the easiest for hill climbing, right, you just you go where the gradient, right, is the steepest. I guess I'll have to go. I guess I'll do paint again, since I don't have a picture here, but I have the book picture, right? So again, to reiterate, right, I'm gonna have a nice clean color, right? So, right, right, something like this, right? Okay, so let's draw a little guy here, right? He is here, right? Right. Okay, yeah. So you see the problem, right? So this is a global maximum. Global maximum, right? And the question is, how do you find it, right? So, and this is like one-dimensional search space. I only have one dimension, right? So again, so this will be local maximum, and again, local max, right? So you go near gradient, or what's it called, dx dy, right? The derivative, right? Ascent, right? So this is, dx. This is x, right? This is x, right? This is y, right? So it will be dx dy, right? Right? On dx dy, right? Did I do it correctly? No. Well, right? So you're going up, right? But again, because we are gods here, right? We know everything, right? But that poor guy doesn't know. I mean, he doesn't know what's all there, right? So what kind of approach? So how do we not get stuck here? So basically, he reached this up. I mean, he will reach this, right? He's not going to go down, okay? Because maybe, of course, maybe there's another peak here, right? But he sees, okay, it's going down. You don't know. But I'm good here. I did the best, right? So, what do you think? What could you do? Assuming, what kind of approach could we take? Any ideas? How could we solve this problem in general? Like the idea, please.
To find the global maximum?
Yeah. At least there are many different things you could do. Yes.
You can say like a value which is like the current max.
Yeah.
And you go through the whole thing and you can.
Yeah. Yeah. So of course, obviously, if we could go through all the values, right? It's just a simple find min, find max, right? But we don't have this option. We can't explore all of the space. That's the problem, right? You say, okay, how can we not explore all? Because notice, this is continuous. This is continuous, right? So you can't really, I guess, you say, okay, this is continuous, right? Best we could do is, right, this is float, basically, right? In infinite values, right? So basically, you say, okay, yes, well, let's see if I'm really, there could be like here, there could be a sharp peak here, right? Like this, right? But it's only like within certain values, right? I mean, it seems like nonsense, but yeah. So, short subs, you can't explore the full search space. What you can do, of course, assuming you could do, you can quantize, right? Meaning this divide in chunks, right? So hopefully you can hear this. Where's my, yeah. So you could, but one approach you could do is, like you said, you could quantize this, right? Say, okay, like do this, like here, basically, right? Right? Okay, and just, find min, find max, linear search, go through, max, this quantize. This is one approach, right? Again, but it's for one dimension, sure, right? But if you get a multi-dimensional space, right? Not just 2 dimensions, 3 dimensions, 4 dimensions, right? Again, it's not going to be so easy, right? So approach, there's all kinds of approaches. Idea being that something, sometimes it might be, okay, you have something good. You find the global local minimum or local maximum, that depends what you want to find, right? Find local maximum, and then you see, one approach is to start looking around, start jumping around, right? So see, okay, maybe there's grass is greener in the next country, right? The next place, we do some jumps, assuming your environment lets you do the jumps, of course, right? So you can jump. You're here, you check maybe here, right? Jump, right? Randomly, right? So there are different approaches actually to this, right? Or maybe, okay, if this is good, and we can climb up, right? So some randomness, it might be an approach, right? And again, it really depends. The question is, it depends on your search space, right? Like again, if it's all discrete, meaning you have numbers, sure, go for the max. Do exhaustive search. Look at all the solutions. Obviously, that's easy, right? Brute force, right? Just go through everything. If it's only 100 values, obviously, check them all, right? But if you have billions or trillions or, I don't know, sextillions values, right? You don't really have this option. Okay, right. So, again, maybe because this is, I'm showing you like a single dimension, it seems easier than it really is, right? So one approach, which I mentioned this, right? So something called simulated annealing, right? So it's a local search. Basically, an idea is this: you let the algorithm make bad moves, right? You have this temperature parameter, right? You might have seen this in again. It appears all over the place, right? There's a temperature parameter and decreases gradually over time. So this is kind of idea. It comes from, I think I mentioned here, it comes from metallurgy. How do you say it in English? How do you pronounce it? Metallurgy? Where's the accent? Metallurgy? I don't know.
It's close enough.
Close enough, okay, but you know what I'm talking about, right? Metals, right? Heavy metals, right? So, I'm not 100% convinced, but okay, I like that better. So, we have this idea is things are cooling, right? Metals are cooling, right? As things cool, you jump less, basically, right? Initially, things are wild, crazy, but then, where's my picture, right? You see it here, right? You start slow down, right? It gets cooler, and you don't let the algorithm make so many wild choices, right? So it's a way, again, working with some constrained movement, right? Does it make sense? Not really. No.
In this visualization, so this is the one you explained previously about finding the maximum and then just...
Yeah, you start jumping. So here I just did random jump, right? Idea is this, that as you are climbing, right, you also do some jumps, basically, right? And idea is this, that initially you're allowed to make really crazy jumps, but then as time goes by, you are only allowed smaller jumps, sort of. And so initially you can jump all over the place, right? And then you see, okay, maybe as time goes by, right, you say, okay, you finally find something that's maybe it's local maximum, maybe it's global maximum, you'll end up somewhere, right? So the idea is maybe by this jumping, right, you might find some good places to start, basically.
Like when you get to the local maximum, the next jump might as well be down there.
Yeah, but the idea, of course, okay, so here's the thing. In this sort of like abstraction or model, right? Again, remember, all models are wrong, right? We are allowed to go back, right? Meaning, if you jump down, you can go back. Okay, you check. Okay, maybe you don't go, you just peek. You send your bot there, like you send your assistant there, right? And let him die. No, you don't want to die yourself, right?
So essentially, the result is that you'll never go lower.
Yeah, you basically check, okay, is this a good place to check, right? Okay, you do these checks basically. The idea being that you check as time goes by, you check less, meaning you don't go, you sort of like settle down basically, right? You're settling down, right? Again, it's not the only approach, right? Again, but because this is like a one-dimensional space, basically, well, 2 dimensions, but basically you have one part, just have X, right? In real life, you may have thousands of X, right? Your space could be basically, not really easily visualizable, right? So this approach actually has certain advantages, but it's not the only one. You can, again, there are other ones too, right? But you can just do, you can always, you can ignore it, you can do just randomness. You can do completely random. Why not, right? So, I've used simulated annealing sometimes, right? So, yeah. So, idea is that you initially you have to accept some more solutions and then you settle down, right? So, yeah. So, comparison with hill climbing is you have a much better chance of finding, getting out of this local maxima, right? So, how it cools, again, this is something to experiment. Depends on different assignments, basically. Now, all right. So. It's very versatile, right? So, local beam search, right? So, you're searching, right? So, with hill, you go up one direction, right? And again, in this example, in our picture, right? Well, we only have 2 or beam, right? We only have beam in 2 directions, right? Sort of like that. But it is you might want to look at a different. You have a multiple. You have 3-dimensional space, right? You have a ton of directions where to check, right? So you start with some random selection, right? And you check whether, you keep checking a couple candidates. Remember our last lecture, we talked about the beam search, like when you're searching for some paths, you keep couple candidates, right? So you're exploring multiple paths simultaneously, right? So what's good about it? Well, again, here I can't really show you beam search on a picture, right? Because here I will have to draw this like basically, in 2-dimensional space. Like I look here, I look here, I look here. I keep, let's say, 3 beams, for example. I check 3 locations, and I keep always checking 3 locations, basically. Right. So possibility. Right. So stochastic, right? So maybe you just select top case states, possibly, right? Yeah, it's variation, right? But you have probabilistic model. You have some probabilities, right? Again, depends on your model, right? It really depends, right? So maybe, yeah, again, so where would you use this? Again, when your search space is too large for full brute force, look at everything, again, right? So, again, you can possibly miss a solution anyways, right? And for really large problems, right, it might be still a large beam search, right? Okay. And then we get to evolutionary algorithms, right? Right. So how do we get from a monkey to a tiger, right? Approach, right? So, again, of course, people are inspired by biological search, right? Biological processes, right? Evolution, right? So you evolve a candidate solution over time. Kind of cool thing, again, right? So, basically, you search, right? Stochastically, right? But you have some sort of what? Fitness. You have fitness, right? You do some approaches, different approaches, right? And you maybe, you combine multiple solutions and you check whether, whether there's fitness. There's a fitness function says, well, how fit your offspring is, right? I want to show you that, what was that funny running game, which had a genetic, running man genetic algorithm. Let me see here. Running, oh, come on. What is this? Why is it red? What is this? No, Valdis. Just because I think it's because I I didn't. I'll do Control Shift N again. All right. This. Okay. So running genetic algorithm, right? Game, I think it was. Right. Let's see. I think you've seen this. Where is it? Like, there's the one which always falls down, right? A mass challenge. I'm trying to see which one. This is a really old one. Like, I mean, old meaning 20 years, not, you know, in terms of AI, that's really old, right? But you basically, okay, you're trying to find some solution, right? So you combine some, again, you have a huge search space, right? You don't have one dimension, you have multiple dimensions. You try to combine something, right? And you have a fitness function which says, okay, this looks pretty good, right? So I want to see some nice, here is, this is pretty good, right? Feature.
I wrote running evolution game, and I think it might be with
Yeah, I think so, running evolution game. Yeah. Yeah, I think this one here is the one. Right, there's a couple variations of this one, right? Lots of them, right? Lots of fun. So again, so you have multiple parameters, right? Not just one, as in our hill climbing, right? But you have multiple parameters to evolve. And I forgot what the game was. Let's see this one here, evolving legs, right? This one's kind of funny, right? So each was on each I/O, was it?
It was evolution IO.
I think so. I think. What's the side? This one?
Yeah.
Yeah. Yeah, I think this one, at least one version of it. Unity. Okay, yeah. All right. You place joints, right? Next, connect joints. Connect bones with muscle. All right. You want some wings? Sure, you get wings. All right. Evolve. All right. On.
That's what you'll have to do. It's like
Okay, that's tutorial. All right, so let's put some points, right? 4 points, okay. These were joints, right? Bone. Oh, no, it is. Oh, yeah. We want some bone, right? This looks pretty bad. Muscle. They want to like this? Yeah.
will this walk?
What?
Will this walk?
I don't think so. It'll die, probably.
The optimal algorithm for this game is just create a meatball. And the meatball was the fastest one.
Yeah, so that's the thing is, evolution works in strange ways, right? So let's evolve. I think this is a very simple example. Yeah, it's not moving. It's trying to move, right? Generation. All right, it's, well, there are some improvements, right? You see these different variations, right?
I propose making more branches.
Yeah, I think this is, I don't know how you can make it fast. Like I said, best of one generation. So I want to make it run, basically, right?
No, I guess it's running. It's just
Very bad.
No, it's trying. Like we got the best of the first generation. Just look.
Yeah. All right. Let's do. Okay, generation 2. This is an improvement, right? Yeah. It's bad. All right. Let's go. Let me try again. I'm not happy with this variation, right? So starting point is important, right? Okay. I think this is actually a good time for break. So again, you can try. Maybe you'll get something which runs, right? Yeah. The ball.
It's a meatball.
Yeah. It's tough. But of course, do you see many meatballs running around the city? I don't know. Right? It has certain other disadvantages. Yes.
Have you seen those videos where AI learns to walk?
Yeah, of course, yeah. So it's pretty funny. Like I said, I mean, that's what it's using, right? No. Well, okay. Yeah. So, all right. So break for now. Let's hopefully this sound is okay, and I will record it.